How are y'all today?
Good.
Good.
I almost died during chemistry.
Oh, well, at least it wasn't on the highway. I thought you were going to say you almost died getting here. I saw like 10 cars on the side of the highway.
Yeah,
So-
dude, what is wrong with everyone? It like barely even snowed. People just abandon their cars on the side of the road.
They've got to get their aggressiveness out before
like,
snow.
Where do they go when they leave their cars though?
It's the Florida way.
They like get rid of them. Like,
They must be driving two-wheel drive
It never
cars.
snows
Yeah,
that way
Yeah, I
like
saw
this.
like 15 on the way down here, just on the side of the road, like on 287.
Yeah, it's ridiculous.
Being in
So-
Colorado, you have to have four-wheel drive. Come on, man.
Yeah, I have rear-wheel drive, so every time it snows, I'm like, oh no. But I'm glad you all made it safely here. Good to see you. So, reminder about our second exam is 1 week from today. So just make sure you're getting your homeworks and your quiz done. Okay. The derivative rules handout. Someone was asking about that last class. So I went ahead and posted this here on D2L under handouts. So there's 2 pages. You've got the basic derivative rules, and then the second page is the derivative rules for specific functions that we've talked about so far. So I mean, I guess when you look at it all together, we really see that we've learned a lot of stuff. That's a lot of material. We're gonna learn the inverse trig function derivatives today in 3.10. But that's there if you just want a quick reference as opposed to thumbing through your notes. Hopefully you have like note cards to drill those because there's just so many of them. But that's there if you need it. Okay. The notation is consistent with what we were discussing in class. Some of them were presented in terms of the chain rule, like for example, this derivative of the log base a of g of x. That's presented in terms of the chain rule. But then the one above it is just without the chain rule, when the argument is just x itself. So again, keep those things separate in your head when you're studying these. Okay. Does anyone have any questions over the homework? We're mostly done with 3.9. We've got one more type of function to talk about. So hopefully you're getting that homework done as well. It's time consuming. So all right. If there aren't any questions, then we'll finish 3.9. And where we left off was talking about these functions that were f of x to the g of x power, that are not really exponential functions and they're not really power functions. So we did look at one method to take the derivative of those types of functions, and we saw that on page, I believe it was page 7. So we saw that here, based off of property number 3 on that first page, we were able to take the derivative of that type of function, but we had to rewrite x to the x as e to the x ln x, and then utilize the property of logarithms. So we took the derivative of e to the x ln of x because we know how to take the derivative of that type of function, and ended up with x to the x times 1 plus natural log of x as the function's derivative. All right. And then we looked at logarithmic differentiation. The process of logarithmic differentiation. Does anyone have any questions on that? So we're going to start off then by having you compute the derivative of that function, again, x to the x, using logarithmic differentiation. So take 5 minutes, compute that derivative, and then we'll talk about it. We do have a means to compare, right? We've taken the derivative of that function using the other method. So once you're done with logarithmic differentiation, compare your derivative to the derivative we had on page 7.
Oh, no, I have my stuff.
See, I'm just doing a longer story. So if I, it doesn't matter which one. I can do it this way. I'm relying on processes, like, it's longer, but I'm a simple creature. So I need simple.
Yeah, I would honestly.
So
Yeah, because remember like if you have the log of y, and you take the derivative, it's y prime over y. But if you introduce this logarithm, there's nothing wrong with introducing that. But remember the derivative of, this is the log base 10. So that will be
now I know that you and my boyfriend could get around
over
homes
y
well.
times the natural log of 10 times y
That
prime.
indicates a change in elevation.
So like if you use the ln, you don't have that extra ln on the bottom. But any other logarithm you introduce, you'll have that extra
You didn't
log
just
of
save my
base
life by
involved in the
correcting
derivative.
me. Like you understood where I meant.
Because you have like one less
You
base.
understood I was changing my location to be in a different location, which is all that I said. Like, all you're proving is that you were pretentious enough to not only know directions, not that that's pretentious, but to feel the need to correct me. Yeah. My boyfriend does the
Now,
exact same
when
thing.
he says up, does he mean north?
Right.
Because that is a very globus point of view.
And then, so you work on this, can you say
You're being very colonialist.
He's being pro-Arctic and anti-Antarctic.
I got to the Ellen.
X to the X because E to the X.
Oh, this part is equal to this, or just the X.
Just the X to the X. You can rewrite it as E to the X element.
So during the break today, there is one problem in particular. In 3.1, it's writing me insane. And I don't want to use the rules, the actual shortcuts, because it's in 3.1 meaning they want us to use the definition of derivatives to solve it. But I keep getting the wrong answer, and I literally spent an hour doing it. So if you guys just help me,
Do you by any chance have it written down?
no, but I can.
No, we'll wait till we're at.
Okay. Because I keep getting like close to the right answer, but not the right answer.
And it's gonna be some stupid algorithm.
Right, yeah, and that's the problem too. But I also didn't want to wait until Sunday because I feel like it's holding me back from the rest of my life. Write this down. Oh, it's too late. You can't just walk. How dare you?
Or no, you can just rewrite ln of y as y times
I'm sorry? There were three that I was having a hard time with. It was, one of them was a square root function, the other one was a quotient, and then one that is escaping my mind right now. But the issue with the quotient was I I'm sure it's some silly algebra rule, but I was having a hard time figuring out how to get rid of the quotient. Right.
Multiply top.
And I did that, and it wouldn't be something silly in my math, or I just would like to work it out to figure out where exactly I'm failing. Because I'm used to in those problems, you're able to factor out h and then cross it off from the numerator and the denominator. And I'm not sure if it's a different way to do that or what, but it's really tripping me up. And it makes me feel silly because it's like 3.1 and I'm like, especially because like in case of something that's a little bit harder like that on the exam, I don't want to be like, oh, I'm using these other ways and not have the math to back it up.
No, it's just.
Also, I was so mad when I went to Walmart, my son was shirt, and then I couldn't, there wasn't one in my size. But there was one in Toby's size, so I picked one up for him. And then as I was walking away, I found it in a different pile. And I was like,
Oh, that's awesome.
Is that one you're wearing?
yeah. I think it's sick. I haven't seen the new movie yet, but.
Basically, more covered, and he's got the tile dye and makeup down here. So it's
I love that.
That's great.
Yeah, it's already roughed out.
So this is writing. Do you find with these pens that like as you're writing, it like gives out? And then you're like,
So just to mention here, when we use logarithmic differentiation, you can use whatever log you want to use, but the issue with, and I guess maybe it's not an issue, but when we look at just y equals to the natural log of x, the derivative of that, we just get 1 over x. But when we look at, I don't know, the log of any other base, like maybe the other common base is 10. So if we're going to take the log base 10 of both sides, there's nothing wrong with that as long as we take the log base 10 of both sides and then take the derivative of both sides, right? So what is the derivative of the log base 10? Of x. Of the base. So that should be 1 over x ln 10. So the natural log, the advantage of the natural log is that it doesn't have that multiplier of another natural log in the base. So that's why I would recommend using the natural log. However, you're free to use whichever log you want. Does that make sense? Okay. So that's my recommendation, is to use natural log.
so is it just gonna like an integral rule that x to the x plus the ln x?
It's sort of the property of, because like e and natural log are going to be reverses of each other. So what that allows us to do is it gives us an e to the and the chain rule lets us take the natural log of this and
You took the derivative of this quotient, and now you take the derivative of this side. Because y prime over y is the derivative of
A little bit. I mean, I think I would have to do that.
yeah, I would
Yeah.
have no
Right. Did Joel get that all right?
That's what I
They're fine. They just take less.
All right, I know some of you are still discussing, but the idea is to take the natural log or the log of both sides. Natural log, like we said, is easier to work with. And then before you take the derivative of both sides of your equation, you need to simplify what you can in terms of the properties of logarithms. Otherwise, you're really not doing yourself any good by using the process of logarithmic differentiation. So we simplify the right-hand side by bringing the power of x out front. And we've only just algebraically simplified that, so that's still equivalent to the natural log of y. So once you've completed the simplifying in terms of properties of logarithms, then that's when you differentiate both sides of your equation. So just, some of you were saying y prime, some of you were saying that y prime over y was equal to x ln x. And that's not an appropriate way to write that, because if you write it this way, what you've done is you've taken the derivative of this side here, but you haven't taken the derivative of this side here. So you're breaking that equality because you did something to one side that you didn't do to the other side. Does that make sense? And so if you're doing that, I think it can get confusing, because then you can say, well, I've got to take the derivative now of x ln of x. Do I need to take the derivative of this side again? And the answer is no, because that wasn't appropriate to write in the first place. Okay. So we simplify in terms of logarithm properties first, and then differentiate both sides simultaneously. And to take the derivative of the right-hand side, we have two functions of x multiplied together. So you've got to use the product rule on the right-hand side. So we have the first times the derivative of the second plus the second times the derivative of the first. Are there any questions regarding that step? Okay. So we have, move over here, we have y prime over y is equal to x times the derivative of the natural log of x is 1 over x plus the natural log of x times 1. I don't know, we'll just say it's times 1 like that. So then we're dealing with y prime over y is equal to 1 plus the natural log of x. Okay. So then what do we do? Solve for y prime, because we're trying to find the derivative. We're trying to find y prime. So we have y prime equals to y times that quantity 1 plus the natural log of x. And then we know what y was. What is y?
X to the X.
Yeah, right, it was the function that we started off with. Y is x to the x. So we'll just put x to the x in there for y. That way everything on the right-hand side is in terms of x. So x to the x, 1 plus ln x as the derivative. And then again, we can check that or verify that with what we did on page 7, that was exactly what we got. Did anybody have any questions on any of this? Yeah.
So logarithmic differentiation is the one where we know that if you are close to the right answer, the original function should be in the answer, right?
Right, right, yeah. So the process of log differentiation, we said that, well, here are our steps. When we solve for y prime in that final step, that always entails multiplying through by this y here. And it's improper to leave that as y, so you just resubstitute what your original function was for that y as the final step. And most of these that we've seen, if you've done any of these yet in the homework, they're pretty gnarly looking. I don't expect you to multiply those out, so just keep the y multiplied by what you had on the right-hand side. Does that make sense? Did you have a question there?
I was able to figure it out. I had to look closer.
Okay. Okay. So now there's really two techniques that we have to take the derivative of the functions of the form f of x to the g of x. We can write that by property 3 on the first page, or we could default to logarithmic differentiation. And I would say that as far as taking the derivatives, whatever process you're more comfortable with, stick with that. I don't think there's anything wrong with looking at both of the processes, paralleled with one another. However, the process that we utilized on page 7 to take this derivative, that process will show up again when we start looking at limits on those types of functions. So it's definitely worthwhile to know this process and how to rewrite it in terms of e to the ln of that function. Okay. So granted, by the time we see this again, you might forget because it is many weeks from now, but I hope this is something that sticks with you because it is really a common thing in higher math. Definitely worth knowing. All right, any further questions on this example? Okay. Well, let's look at one more. So the x to the x is basically the simplest type of function that you will see is f of x to the g of x. So let's look at one that's a little bit more involved. Same instructions as above. So our function is the quantity 1 plus 10 over x to the x. And we want to find the derivative using logarithmic differentiation. So why don't y'all take take 7 minutes to work that one, and then after we've looked at this logarithmic differentiation process, we'll look at it in the other light where we use property number 3.
Well, those- I'm stuck already.
Probably deep in thought. I know, I'm trying to see where I'm going with this flow
They're
stuff.
not like that.
So like, it's probably here. So it's like, so at this point.
I just,
Or do you just want to take a picture of them?
I find it miraculous that I.
Technically advised against taking a derivative. Yeah, I was writing this out and I was sitting there stopping, I got to this before the end.
Yeah.
And then bring the Y
I feel like I
up.
want.
Yeah.
Combine everything and see if magic happens.
Yeah, right, you really, right, and then so you see the problem, like the bulk of this problem is taking the derivative of that thing, right?
Right.
Well,
So that's
so-
what I'm trying to look at this.
You know what the log rule is when you multiply and divide. What about math?
There is no.
No, so that's, that again, right there, it's a product.
No.
No? Okay.
Because there's no laws on that.
You couldn't do ln 10 minus ln x.
Well, I was thinking,
There's no way to get it by itself without the one plus.
well, but that's why I was thinking you would
That's
do
there.
x ln x 1 plus 10 minus x ln x.
Well, so
1 plus.
as ugly as it is.
So, what I would do for the step, just to clean it up, is to write this x to the negative 2, this 1 over x squared. Yeah, because this x squared here.
I feel like I could clean that up
cancel
without
out
the
the
rows.
rows. And then you can clean up the problem with what's left over.
You get 3 terms multiplied by 10.
Because I will always pull out.
Oh, that's the derivative of x. There should be a 1. That's why there's one. You just got rid of the 1.
Would this be a plus here though? Is the product rule?
Yeah, you're bad. Barely. No.
Because I pulled it out from.
So,
It's not a constant though.
yeah, but when you went from here to here, you did the product rule, right? FG prime plus F prime G. What did you do?
A second conversation.
Alright, so right here, you take this.
Yeah, you take the x and you pull it out.
Okay, now you take the derivative of both sides. Derivative of this, so this is a constant. You can just.
No. Where are you getting a constant? Right there.
And where are you getting the 10 from the 12?
Yeah, where are you getting the 10?
So then, you take the derivative of
Oh, I didn't do that chain wrong.
This guy's
Yeah, that's right. I didn't get that chain wrong. I think that's a plus. Okay. Yeah, there should be a plus because you're.
Then, if that's the case,
It's a change inside of the
it's still gonna be ugly.
Yeah.
You know what's up.
I didn't do that chain wrong.
Oh, I think I should go somewhere.
So this is. Did you put
You're very blessed.
Oh, gosh. Okay, yes. Yes. All right.
I have no idea where to start.
Well, you did start it correctly.
Yeah.
Yeah. So what can you do, if I have the log of something raised to the power, what can I do with that?
Is that the chain rule?
Well, I'm not, at this point, I'm not taking any derivatives.
Yeah, that, the 10.
So I can hold that out front.
Right.
Okay, so then that would be
Oh, I see, because that's split.
Like that?
Yep.
Okay.
And so things like weird function, you can turn it into just a product or two functions. That's the advantage of this.
And then we use the product rule.
Yeah, the product rule.
Oh, okay.
So it
So
would
that's your
be,
first integer.
Oh, okay, got it.
okay, so the ln, all of this is the second.
Exactly, yeah, which again, you have a number, you will when you take those.
Okay.
Oh, museum X.
What do you get?
Oh, man. I've gotten so much. No, my brain's
No, well.
my brain's still on. Chain rule and doing all this stuff.
Yeah.
So there's just like, please don't make me go on right now.
So the
I'm
product.
just gonna stare at your beautiful face and try to figure this problem out.
I don't know what I'm
I mean, if I'm staring, I'm seeing through you, the nether world,
Yeah.
ether. So like, you're watching.
Oh, that's not.
I'm not trying to
Yeah, it's not gonna be wide.
yeah, stare at things. It's all, I can see nothing. And there's the first. Like I see things, but everything else is in front of me. Yeah, something else is going on. So my mind's more, I would describe it as good as this. Mine's more shitty. There's a weird one here.
Which is not equal to that. That's my own. Yeah, that's the year that I have.
Those two things.
Oh, I just have that. Oh, okay, I just have that written right. I have it as 1 plus 10 over x. Yeah, it re-simplifies it.
In the same.
Oh, I see.
So how would we find, so this would be a change.
Yeah, it's normally easier to have the x term first. Yeah, because I took this, but then it's
That seems like a you thing, not a me thing. I don't
Yeah.
Yeah, yes, because we get one times technically divided by 0 to that would work. So we couldn't compare the two things because one is existing. We could solve that problem.
I think the outside direction would be
Too old, you're 75. Great. It's like,
the derivative.
I mean, even so.
Oh, is the x included in that?
Half an
No, sorry, I'm not talking to anyone at this table.
Let's just say.
the derivative of ln. We just did that, right?
And then that's this.
It's 1 over.
Okay, so I'm gonna just think about it for a minute. Okay, so the ln y product rule is
What's the
x
derivative of ln?
1 over
and
x.
first, second, second.
So it would be. Well, then we have to.
The derivative of this would be 1 over 1 plus 10, like.
No, it does.
10.
That's what we're looking at.
Natural log?
Would be the
The derivative of the natural log of anything is 1 over the thing.
blue eyes for a little bit.
So like there was natural log of that. It would be f prime of x over x.
It's hard to articulate.
That's only if it's y. That's only when it's f of x though, because then it's talking about y.
I know,
this
that's
is
what
in
I'm
terms of
doing.
x.
So what's-
Yeah, so it's a natural log of a function of x. So it's the derivative of
Because you're doing the
whatever
derivative of the
inside
outside, the
divided by whatever's
inside
inside.
times the derivative of the inside. That's what it says right here. The derivative of the outside
Yeah,
times.
but no, that's not times, that's that inside of the outside still.
Hey, look at that, like, the
It's
y.
not times, so when you have like, this is f of g of x, so you plug in g of x
wait.
to f,
So you would just get rid of that and then.
Do y'all want a few more minutes to
Yes, please.
discuss?
yes.
Okay.
We're
And it's,
trying.
if you're close, then it's hard to just let it go, right? You
Yeah.
gotta figure out the puzzle.
There's two incentives. One is this, okay, so this right here is, okay, so we're taking the derivative, and so I'm using the product x times the natural log of this. So I've got
What part
x
are you on?
times.
Where are you at?
I made
So
it
the
the
entire
product rule.
derivative is 1 over all of this. And then you have to, so this is 0, so we don't have to worry about that.
No, that's why we made it. I just did the derivative of ln 1 plus 10 over x, because I thought it was 1 over
Times
1
the
plus 10
derivative
over
of
That's
x.
what I had to
is
do.
0.
But I think
Minus
if you don't have that, then
the top, which is
I don't know. I don't know if that's right or wrong.
Yeah.
And
I had
then,
originally.
so if you take the derivative of 1 plus 10 over x, that would be 10.
plus,
Like with the extra term.
Yeah, that's what I had, that's what I had.
Okay. That's what I was thinking, but I had.
so then you end up with
But I don't know what to do about
10x
this.
over 1 plus 10 over x plus the natural log of 1 plus 10 over x. And you still got the y over here.
Then you want to just have the y.
So then you pull that over, and that's multiplied times the entire.
So the derivative, if you're gonna do the quotient over there, the derivative is 0 plus the derivative of 10x to the negative.
No, but you have to do the change in terms of x. So you just take the derivative.
So
That's the
That, yeah, this part trips me up. I don't get the 10 over x. Do you do the quotient rule? Do
I
you
don't know.
not?
Yeah.
So I took
Because it's in terms of x.
Is it
I thought
1
that was
over-
in terms of y.
So I did the bottom,
Is that what you're
times
supposed
the
to
derivative
do?
of the top, so x times 0 is 0. And then
That's what I
minus,
Because I mean, you could do it. You could get the quotient of this.
that gives you
but-
my negative 10.
So, but you would wanna do the quotient rule on the whole, the 1 over. So if you're just doing the.
Would I do
quotient
a
rule-
quotient rule on this one, or would I just shrink it? So I'm doing the quotient rule, and so I'm doing, taking a derivative here and then doing the chain rule of doing the derivative of that.
Say that again.
Okay, so the way my brain worked, so I was like, okay, I'm going to do cross rule here and here. And when I'm taking the derivative of this one, I'm using a chain rule. So I'm doing this one and then I'm taking the derivative of this one. I'm ignoring the one because it's some.
Okay, I see. So you have the first times the derivative of 1 over this times the derivative of your argument, so it's 0. And then you're using the.
Then I'm using the quotient rule inside that, which this is the entire quotient rule here.
All over the bottom square, right? That's what you're using.
Yes. Damn it.
ln 1 plus 10 over x.
Oh, you can't.
Like, I think I'm literally the most wrong that I've ever been in my whole life. But at least I'm doing something.
Okay.
Do you end up getting? Oh. How'd they get that from you, Hal?
Well, also you gotta remember they're probably dividing through.
Oh, that was step, okay, that helps. I thought that those words are steps, and I'm like, wait, how did that happen? Okay. That one times the take. So you do use the chain rule.
You use a case.
Yeah. So it's the, so it is 1 over
That's fine. You know
1
what you're
plus
doing.
10 over x
Keep in mind that all this right here is.
times the derivative of 1 plus 10 over x. You take the derivative of the whole thing minus the times the derivative of x. Oh, they put it all on the top of the fraction. Oh my god, why did you do that?
Okay. That makes sense.
I'm gonna calculate here.
And then you bring that forward.
They put this on top of the
Literally
fraction.
exactly what I got.
Cool.
But I
Oh,
don't feel like
that's what they did.
I'm cool.
With the derivative still, they didn't do the
I think they use the quotient rule to do.
Oh my goodness.
Let me get my.
Okay.
It's very hard to read because they only 10 times.
I don't know. I have an answer that I got, but I don't know if it's right.
I mean, if we did that, it would
You
be.
have the X right here.
Do they pull the 10? Oh, they pull the 10 at constant. Oh, I see what they mean.
He's gonna check my answer and then.
Yeah, they did it as, they moved the 10 over x in front, so they made it as 10 times 1 over x plus 1. So then the 10 is constant. Simple thing,
They
they
just
can
put a
just pull
1
it
above
out,
the
yeah.
x.
And then it's
Yeah, because when you
10
distribute the x in there, you have x plus 10 that you
1
Or
over x.
you could, something, if these x's cancel out, we just have negative.
I have
Still over
x
10
10 times x.
Plus 1, and then they just pull the 10 out. You can do that, right? You can move the 10 in front of the
Closer than
derivative.
I thought.
So you did
Like this.
So you did 1 over this,
10 out here.
So, okay, so
Pretty sure,
derivative
yeah,
of
because you just times it by constant, you can pull that out, so then you have 10.
because that's
And
10x to the
then
negative.
the derivative.
The derivative of 1 over x
So
plus 1.
that's gonna be an x squared.
And would you use
divided by this
the
x.
quotient
Still gives you
rule, or would it
x
just
in
be
the bottom,
1?
right?
Yeah, they end up with 10 times 1, so I think they just put it in x of 1, 1 over 1 is 8.
Oh, like the derivative of 1.
So I did.
Correct.
You made the exact same mistake.
I think it's 0 somehow. Wait,
Yeah,
no,
the bulk of that.
Oh, because when you take the derivative of 1, that's 0.
Yeah.
1 over 1 plus 0, which is then 1. The general form on the top is 0.
So, okay.
So it'd be 10 times 1, basically.
Yes, on top.
Because
And then I'm like, we still have the 1 plus 10 over x on the bottom, right?
so we have to do
Where do they get that x squared from?
this
I'm
derivative,
confused.
and then we
That's
go
what they were
inside,
talking
and
about.
we take the derivative of something else.
Where does that come from?
So when we're taking the derivative of 1 is 0, the derivative of x since it's known.
Yeah, I also have that.
Because it's
So
up there.
it's this one.
What do they do with that?
How did that come to be?
How did you guys get the x?
Where does the x squared?
That's where we're. That's where
When you
we're
take
So it should be right here.
Wait.
So why is that one squared? Is it the whole?
Okay, so when you're doing the derivative of this, it's the bottom. So bottom times the derivative of the top.
Because right now all we're working on is
Minus the
Yeah.
top times
Yeah,
the
everything,
derivative
we
of
both
the
got
bottom.
to their, now we're stuck.
we're working on
Divided
that.
by
And we don't know how they got x.
Oh, cool.
I think
That's where, it's just the quotient
It's,
rule.
it's literally the quotient rule, and I screwed up. I did it all the top, and I forgot the bottom.
Gotcha. Okay.
I'm looking for it, so I can.
it's the second times derivative first minus first times derivative second all over the second squared. What's
So
the
that's
second
the
I
x
minus
on
I
top.
d low
Yeah.
all over the square?
So that's where right?
That makes sense.
First
Or is it that whole thing?
Where did I get the 1 from?
The one we figured out was the,
Yeah.
that's,
I feel so. But also,
Oh, because they pulled the
my
10 out.
brain was like,
So the 10 is now null and void.
not in like a good way, in like
Then
a.
it would be,
So my strategy is I just break it up into itty bitty little pieces, and I don't care what the final product looks like. I just take.
that's 0, the derivative of that 0, so the derivative of 1 over x is
And then I'll do the
second
algebra.
times derivative of first, which is 1, which will equal 0,
And the
minus
way I see it on an expansion,
1 times the derivative.
That's true.
with the wrong answer, this is what 3 plus 2 is.
This is going to be
This isn't
negative 1
entire
minus all over x
My
squared.
thing is, and like sometimes it trips me up because sometimes I write out too much and then I, but I write out.
Then you have, then you have 10 times negative 1 over x, which is negative 10 over x squared.
That's what you're that's your one.
Same exact thing. Oh, yeah.
And then that's that. And
it's just negative 10.
then that's that.
Oh, so it's 10 over 10.
So then you put that in, and then you have,
Okay.
where does the x, that x go?
Bring a y over here.
Oh wait, no, when you take the
Well,
derivative
so
of that, then
first of all, you
want
should
my
probably
lunch?
do the first times
Where are you
the
stuck?
second times the derivative of first. Is that this? Right. Yeah. Okay.
So I'm
So
still
what's
working on
happening
the derivative of
Okay, so that's
Needs
the
to
change.
be because that's part of the
So-
function, right? So you should have the ln
So,
of 1 plus
like you said, it would be 1 over this, plus the derivative
Now you gotta
of
take the derivative
this,
of natural log.
which would be 0 plus,
Your-
and then I did the derivative of
your-
10 over
this is
x
what-
over here.
Yeah, so
The only thing I messed up on was this was supposed to be squared the whole time. Right.
So this is a different, this goes to the
the
quotient.
natural log of something is 1 over that thing times the derivative.
And so that,
So all you can have right here is the derivative. You still need our g of x to match.
she doesn't matter.
No, our g of x is what we're taking.
10 over x.
If we're
Or
if
no,
we're
it's
looking
top
at
and
it.
bottom. So it'd be,
So it would be low D high, high D low.
Yeah, that's what we started
yeah.
with. Right.
Question
But
is,
if we're just focusing specifically on the natural
So
log
we
of
would
this
get
mass,
low.
that's where we're at. The natural log of some function. Our function inside here.
that one's got it.
So you have the derivative of the inside right there. You still need
And then all
the
over
derivative of 1 of that.
bottom square.
It's weirdness.
Okay, and then you would have
That's
that
still
equal
correct.
to
That should still be correct.
times 0.
Yeah, so it'd be,
Minus 10.
yeah, it would be L10. You would have,
So would that
you would
come out
have this.
to, okay, so that would come out to this, negative 10 over x squared.
The derivative of that is 1 over this.
Okay, what do I do?
So then you have to plug those derivatives
Which
back
you already
in.
have. You have that right there.
So
You just need I think that's what
you have
did on one side.
x times
Yeah.
negative 10
You were missing.
x squared. But then you have to remember that this was part of a separate.
All right, everyone, can we bring it back? If you're still working, hopefully your questions can be resolved. So if you'll notice the process of involving the logarithm, it turns this funky, like not exponential function, not power function, into a product. So using the natural log, we just have a product of 2 functions of x instead of raising it to the power of x. So specifically for these problems, that's why the logarithmic differentiation is beneficial. So we have the product of 2 functions of x is the ln of y. So we're going to differentiate both sides. Derivative of ln y is y prime over y. And most everyone is comfortable with that, saying that the derivative of the natural log of something is 1 over its argument. times the derivative of its argument. And so it isn't any different when we take the derivative of that natural log there. It's the same thing. So we've got to use the product rule here, where we take the first times the derivative of the second. Plus the second times the derivative of the first. Because the overall structure of this function here on the left is a product. So when you're doing these rules, don't get ahead of yourself. If you see like, oh, it's a product and a chain rule, you don't want to do the chain rule first, because if you do the chain rule first, you're only addressing the logarithm part, the ln part. Does that make sense? You've got to look at the overall structure of the function as a product, and then take the product, the derivative of the product using the product rule. Any other subsequent derivatives that show up is the ones that we're going to compute off to the side. And if any other derivative rules show up there, then that's fine. We'll just handle those on an individual basis as opposed to trying to think of all of the derivative rules at once. Okay. So let's go off to the side so we can compute the derivative of the natural log of 1 plus 10 over x. So like you told me, the derivative of ln y was y prime over y. The derivative of the ln of this thing is 1 over the argument times the derivative of the argument.
It's almost like a modified chain rule, isn't it?
Yeah.
It's just your f prime of g of x is just 1 over the argument.
Yeah.
Instead of the f prime.
Right.
Okay.
So is everyone okay with this? I know it looks different, but in all honesty, if you want to think about this right here, that's your y prime, right? Because that's the derivative of this thing here, and this is your y. So you have the y prime over the y. It's just our y in this instance takes a different form. So if you're saying the derivative of ln of y is y prime over y, you already know how to take the derivative of that. It's just you've got to make these connections when it's different, because these things on the inside could be anything, right? It could be just big, giant, nasty looking function, but the process to take the derivative is exactly the same. Okay, so the derivative of 1 plus 10 over x, some people treated 10 over x as a quotient and did the quotient rule, which is totally fine. I think it's a little bit more efficient to think about 10 over x as just 10 times x to the negative 1, and that way we can just use the power rule on that. So we have the 1 over 1 plus 10 over x times the derivative of 1, which is 0, times the derivative of 10x to the negative 1. So that's negative 10x to the negative 2, or negative 10 over x squared. So any questions on that particular derivative? Or that's just part of our overall derivative. So it's like derivative inception, right? Derivatives within derivatives within derivatives. Okay.
Do you feel
All right.
as lost at the end?
Do what?
Do you feel as lost at the end?
I guess you could, for sure, especially when you're first starting out this journey. Yeah.
Spinning on the table.
Yeah. All right, so then we're going to take that and put that in place.
How does it become negative?
Which one? Negative? The negative 10?
Yeah.
Because it's negative 1 times 10
Oh,
x
you
to
pull
the
that out, yeah.
negative 1 minus 1 power. So let's take a snapshot of that. Okay, so there's that derivative. We still had that multiplied by x plus ln of 1 plus 10 over x times the derivative of x, which is just 1. So just keep in mind that that is still y prime over y. And so some of you just left it like this. You kind of didn't want to mess with the mess here on as the first term, which I think is okay. But again, we can do a little better than what we have right there for that first term. Okay, so one of these x's, this blue x with this x squared on the bottom, one of those will cancel out. So this x will turn this into an x to the first. And then that x to the first on bottom multiplied by 1 plus 10 over x will also get rid of that funky fraction 10 over x. So then we're going to take this x to the first and distribute it to this other denominator here. So we end up with just negative 10 over x times 1 plus 10 over x times x. So that's much nicer looking than what we had originally. Still this term hanging out right here. And remember, what was this? What was all of this?
Equal to y prime over y.
Y prime over y. So this is still y prime over y. And we got sloppy here. This is y prime over y. It is common in math if you're just rewriting the same thing, simplifying, just to put the equal sign. You don't technically have to keep writing y prime over y prime over y. But I think there is tendency to forget what you're actually dealing with if you don't do that. So I would recommend doing that. Okay, we're going to move this down. So we just multiply what we have on the right-hand side through by the original function y to solve for y prime. I'm going to move this and then we'll look at that. So this was like our side work, intermediate work for that problem. So y, we're multiplying through by y. The original function was 1 plus 10 over x to the x times all of that stuff we had on the right. And there's our derivative. That board is bright. Does anyone have any questions on that? Most everyone had, I would say, the majority of that, but if you're missing one little piece, the whole thing's off, right? You don't put a man on the moon, you put a man in space, or a woman in space all by themselves, floating out in the ether. So, I mean, we're not dealing with stakes that high, of course, but maybe one day in your career you will be. So, anyways, just be careful. There's a lot of details. So, we all okay with that? We're going to close that chapter. All right. Okay, so there's a couple of these in your homework as well. Practice those. There will be some of those on your exam. And as always, if you have any issues, let me know. I'm happy to just do more of these in class, because we will see these again in Chapter 4. Okay. All right, before we take our break, just where we're headed next with 310, we're going to talk about the derivative of inverse trig functions. So everybody's favorite functions, right? Everybody loves inverse trig functions. Hopefully, when we sort of introduce this, we can make them less scary because it's probably been a while for some of you since you've seen inverse trig functions. So we'll talk a little bit about those and then look at their derivatives. Okay. So any questions before we head off to break? Yeah.
We're gonna do the problem we just did as the
Oh yeah, we can come back to that for sure.
I
So.
don't know how to write it.
Okay, yeah, I think, so then maybe before we go off to break, I did say we would do that, but this problem did take a little bit of time. Yeah, let's just look at that, and then maybe leave this as an exercise for you to do, and if you get stuck, then just ask. So we did say we would look at this problem. Thanks for reminding me. Totally forgot. We would look at this problem. Instead of taking the derivative using logarithmic differentiation, we would look at it through the lens of property 3 on page 1. So that entails us to rewrite this function using property 3 on page 1. So does anyone want to take a stab at what that would look like? Mike?
So it's e raised to the x times the natural log of 1 plus 10 over x.
What do y'all think? Get a thumbs up back there. Anybody else? So we just bypass that intermediate step, but that's what we do. Remember, e to the it's all we're utilizing is e to the natural log of whatever this is. By inverse properties of those two functions, all that is that.
With the x in the front.
And so what we're dealing with is we're just saying, well, I'm going to say it's e to the 1 plus 10 over x raised to the x, sorry, e to the ln of that raised to the x. So that's just e to the ln of my function. And then I notice again on top, it's the property of logarithm. I have the log of that thing raised to the power of x. So then the power of x comes out front to multiply that logarithm. So this is where we want to start. After we've rewritten our function, then we're just going to take the derivative of it. Remember, the derivative of e to any power is e to the power times the derivative of the power. So it's still e to this thing. So there's e to the power times the derivative of the power. So I hope we've done the derivative of e enough to where that's very solid in your mind. And the only difference here is that when we're done computing this derivative, we've already actually computed that derivative prior to in purple. The only difference here is we're going to change this e to the x ln of 1 plus 10 over x when we're done back to the original function, because that is y, and y is 1 plus 10 over x to the x.
In that derivative at the bottom, shouldn't there also be an x in for the natural log?
Oh, yeah.
Oh, yeah, thank you.
X
Yeah, we
ln.
forgot that. So, yeah, the derivative of the entire power, yeah, thanks. So if you want to try that and verify that it does give you the same derivative, I think it's worthwhile. If you get stuck, just ask. Any other questions or comments? Okay, so we'll take a break. I guess a few things to sort of, as a preamble to this section. The inverse trig functions were, as they say, the inverse of the trig function. But when we look at an inverse trig function, the argument of an inverse trig function is not an angle, like when we say what's the sine of 90 degrees or what's the sine of pi over 2, giving us the opposite over the hypotenuse. When we look at the inverse of that process, we're actually going to input the opposite over the hypotenuse, and it's going to tell us what angle created that, right? So the inputs for inverse trig functions are numbers, and the outputs are degree or radian measures or angle measures. And the way we sort of arrived at the inverse trig functions was, it was somewhat technical, but you started off with saying, all right, well, here's the sine function. And if I want to ensure that I have an inverse of that, the thing that you looked at in pre-calc or maybe algebra was that for something to have an inverse, the function had to be 1-to-1. In other words, if like, you know, the famous function that's not 1-to-1 is just the quadratic, x squared. Because if I plug in an x value of 2, I get a y value of 4. But also if I plug in an x value of -2, I also get 4 as well. So you've got two different x values giving you the same y value. So it's not a 1-to-1 function. In other words, if I plug one thing in, one unique thing in, I get one unique thing out. So we said with functions like x squared or sine or cosine that weren't 1-to-1, we had to restrict their domain so that they were 1-to-1 before we talk about the inverse function of that function. Because we can take the inverse of x squared, but what we're left with is something that's not a function. Because we don't want to deal with those things because they're not functions. So the same idea applied to our trig functions. Sine and cosine were not 1-to-1s. So we said before we look at the inverse, we want to ensure the inverse is also a function. Therefore, we have to modify sine and cosine so that they are 1-to-1. We said just forget about this part, all of the rest of this part of the sine graph. And then we said, all right, well, if we did that to the sine function, now the sine function is 1-to-1. Now we know when we talk about that inverse, it will also be a function. And the kind of the biggest concept behind a function versus its inverse is that interchanging of x and y. So on the function, the domain becomes the range on the inverse, and the range on the function becomes the domain on the inverse, because the x and y have swapped places. And typically those were restricted, like the way we chose, it might have seemed arbitrary, like, well, why would I choose that part of sine? Like, why not choose, why not choose this part of sine so that it's 1-to-1? And that's totally doable. It's just the way we kind of modified their domains is just the more universally agreed upon way to define those. So in the sense of dealing with the sine function, we said we have to restrict its domain from -pi/2 to pi/2, and the range was still from -1 to 1. So that's the sine function. I'll end up erasing all of this. It's not, hopefully some of it you remember, but. So then when I looked at the inverse sine, or sometimes people like to use arc sine. Well, when I look at the inverse sine function, the domain of the sine function, y = sine of x, now becomes the the domain of sine rather becomes the range for inverse sine. So the domain becomes the range, and the range from -1 to 1 on the sine function now becomes the domain or the input for the inverse sine. So I don't know if you remember any of that, but that's how those things that's how they came about. So before we look at derivatives here, let's just remind ourselves for each inverse trig function what the domain and what the range were. So we'll have our function here. The domain and the range. Okay, so for inverse sine of x, we saw that the domain was from -1 to 1, and the range was from -π/2 to π/2. So the domain and the range of these become important if we're once we start talking about how these derivative formulas come about. The inverse cosine had a domain of also -1 to 1. Inverse cosine's range was from 0 to pi. We have inverse tangent of x, whose input is all real numbers, but outputs are from -π/2 to π/2, not including π/2. So if you remember the graph of tangent, tangent had vertical asymptotes at -π/2 and π/2. So the vertical asymptotes on the graph of tangent would turn into what on the graph of inverse tangent? Horizontal asymptotes. Okay. Inverse cotangent has a domain of all real numbers. And the output or the range of inverse cotangent is 0 to pi, not including 0, not including pi. And the sort of the weird ones here, the inverse secant. Inverse secant had a domain where the absolute value of x has to be larger than or equal to 1. And maybe we can think about it this way. Since secant is 1 over cosine, the inverse secant is 1 over the inverse cosine. So we look at inverse cosine and say, okay, well on the interval from 0 to pi, inverse cosine rather, or cosine itself would be 0 at π/2. So if I have that being 0, then I have 1 divided by 0, which can't happen. So the inverse secant's range is from 0 including 0 to π/2, but not including π/2, because that would cause us to have a division by 0. Union π/2 to pi, including pi. And inverse cosecant has a domain also absolute value of x has to be larger than or equal to 1. And it outputs similar to what inverse sine outputs, except for we can't divide by 0. So sine is 0 in the interval -π/2 to π/2. Sine would be 0 there at 0. So we've got to exclude that from the output of cosecant. So we go from negative pi over 2 to 0, not including 0, union 0 back to pi over 2. And worth maybe pointing out that when we say the absolute value of x has to be larger than or equal to 1, we mean two things. We mean that either x is larger than or equal to 1, or x is less than or equal to negative 1. So the input for inverse secant and cosecant are these numbers here. We include that, but all of these numbers, include that, and all of these numbers. So that's our visual way to interpret absolute value of x larger than or equal to 1. Basically, we're not including any numbers in between negative 1 and 1. So maybe a brief refresher there, but all of these things are, let me add another page here before we look at the rules. All of those, some domain and range of each one of those functions do come into play, especially the range, when you're actually deriving the formulas for the derivatives of these functions. We won't do all of them. We'll just do one of them, and just to kind of get a sense of where the derivative formulas come from. But all of them are sort of reasoned through in a similar fashion to this. So if y is the inverse sine of x, and we want to know what is the derivative of inverse sine of x, really the definition of the derivative is one option. We could say, well, what's the limit as h approaches 0 of the difference quotient for that function? The other way we could look at it, we could say that if y is the inverse sine of x, then x is equal to what? If y is the inverse sine of x, what is x?
Something in between negative 1 and 1.
Okay, yeah, I think it's at this point we could say since we are dealing with the inverse sine function, not quite 1 over, but here let's just say that x for this function y is the inverse sine of x. Like we said, x is a member of negative 1 to 1, and y is in what interval?
Negative pi over 2 to pi over 2.
Okay, so we've got to remember that, because that's the thing that we're actually dealing with. That's where our x's and that's where our y's are. So anything we do anything we do from this point, we have to remember that our x's and y's are in those specific intervals, because we are dealing with the inverse sine. But if y is the inverse sine of x, solving for x would entail us doing what?
Implicit differentiation, or whatever that was.
Right.
Just with x instead of y.
So what would you do? Like, what would you do if I said y is the square root of x? How do you solve for x?
Square both sides.
You square both sides. Why do you square both sides?
It negates the square root. Inverse of square root.
Because it's the inverse operation of taking a square root, right?
Still the same thing.
So how do we solve for x and inverse sine of x? Well, we have to involve the inverse of sine. The inverse of inverse sine, which means, and if we have this equation here and we're trying to solve for x, oops, let me leave some space, then what I have to do, just like when I solve for the square root of x, I involve the inverse of the square root. To solve for x here, I have to involve the inverse of inverse sine. So I'm just going to take the sine of both sides, because the sine is the inverse of inverse sine. So if y is the inverse sine of x, then that means the sine of y is x. So instead of working with the actual definition of the derivative, we have sine of y, which again we know is a function of x, equals to x. We can take the derivative of that implicitly. So we're going to use implicit differentiation. So what is the derivative of sine of y when y is a function of x?
Cosine y times the derivative of y.
Right, cosine y times the derivative of y equals the derivative of x. And then so we solve for y prime. So we know that y prime is 1 over cosine y. But the issue here is we need cosine y in terms of x. So what's relating y to x for us so far in what we've done?
What y equals?
Y equals inverse sine of x.
Y equals inverse sine of x, right? Which means that sine of y is equal to x. So if we have any hope of expressing cosine y in terms of x, then we first need to express cosine y in terms of sine y, because sine y is x. Okay. So express cosine y in terms of x means really, as an intermediate step, express cosine y in terms of sine y. So what relationship do we have between sine and cosine? I mean, there's a lot, but what's the most fundamental relationship between sine and cosine that we have? Not derivatives. We wouldn't want to. It's true though, but we wouldn't want to involve another derivative here. That's kind of why we wouldn't do that. There's a famous old mathematician guy. Has a theorem named after him.
Pythagoras.
Pythagoras. The Pythagorean identities relate sine and cosine together. So we express cosine y in terms of x by expressing cosine y in terms of sine y by the fact that sine squared y plus cosine squared y is equal to what? 1. So I need to solve for cosine of y. I'm solving for a square, so it's the plus minus square root of 1 minus sine squared. What is sine squared of y? Yeah, that's
1 minus cosine.
yeah, that's true. But remember, we said we need cosine in terms of x, which means we need cosine in terms of y. Sorry, sine y, because we said sine y was equal to x. So what's sine squared? X squared, yeah. Sine y squared is x squared. Plus minus the square root of 1 minus x squared.
Y equals the inverse sine of y, so what is that? How does it get from the inverse sine to, because it's sine squared,
Uh-huh.
so like how's that
Because
also
we
equal?
took the inverse, so in order to get x on the other side of the equation, since we're solving for x, we had to take the
Oh,
inverse
that.
of
Oh,
sine,
yeah,
which
yeah,
would
yeah,
just be
yeah.
sine, and multiply that
I
with
was
both
looking
sides.
for that one, yeah.
Yeah. Okay, so that's all well and good, which that would tell us our derivative rather is 1 over the positive and the negative square root of 1 minus x squared. But we don't want two different derivatives if we can avoid that, right? So can we avoid the plus and minus root here?
So the absolute value.
Yeah, we could say that absolute value is involved, but we wouldn't want to do that if we can avoid that as well. So, everybody okay with the fact that 1 over cosine y is actually 1 over plus or minus square root of 1 minus x squared? So here, when we look at 1 over cosine y, we really could have said, well, we're taking the cosine of y, but where is y? So I guess question. What do we know about cosine y, which we saw as equivalent to this right here for the time being anyways. Maybe it stays that way, maybe it doesn't. What do we know about cosine y for, like we said at the very, very beginning, our y values in the interval negative pi over 2 to pi over 2. Because y was really the output or the range of the inverse sine, which is that. So what do we know about cosine y for these y values? Do we know anything about it? We should know something about it, but 0 on the endpoints, right? What about all of the values in between? Yeah. So here's y. Sorry, here's cosine of y. And our inputs are just some y values. Here's the graph of cosine. Right? In particular, cosine in between negative pi over 2 and pi over 2. Cosine of any of those values is either 0 or positive. So why is that a good thing for us?
Because we only have one derivative.
We only have one derivative. So let's just write out our answer. Our answer is, our question was, what do we know about cosine in the interval negative pi over 2 to pi over 2? The answer is cosine y, which is our square root, is always positive. Or 0. 0. That is, cosine of y isn't the plus and minus square root. It's just the square root. Since it's always positive, no way it can be negative square root. Therefore, what we have if y is the inverse sine of x, the derivative of that is just 1 over the square root of 1 minus x squared. And that's what you see on the next page. The derivative of the inverse sine is 1 over the square root of 1 minus x squared. If you don't follow that, that's fine. We just need to remember the derivatives, not how to derive or prove that the derivatives are what they are. More? So I'm just going to erase this because it doesn't really make a whole lot of sense at this point. Okay, so that's how we would get all of these. Here's 6 more derivatives that you have to remember. Thanks.
Thanks for that.
You got it. Honestly, just like with the trig function, sine, cosine, tangent, if you know their derivatives, you know the other 3. Same thing here. If you know the derivative for inverse sine, inverse tangent, and inverse secant, the other derivatives are just the negatives of those. So notice we said we showed the derivative of inverse sine was 1 over 1 minus x squared to the 1/2. The derivative of inverse cosine is just the negative of that. It's just the negative derivative. Remember the inputs or the domain for inverse sine and cosine were the closed interval from -1 to 1. Here we say that when we're looking at the derivative is defined only for values strictly in between 1 and -1. And we see exactly why that is, because both 1 and -1 and cosine, inverse cosine, and inverse sine's derivative cause us to divide by 0. Derivative of inverse tangent is 1 over 1 plus the argument squared. And so the inverse cotangent's derivative is -1 over 1 plus the argument squared. So they're opposites of one another in that particular way. So really, you get 6 for 3 if you can remember those 3, and the fact that their co-functions are negatives. The reason that the inverse secant and the inverse cosecant have the absolute value involved in their derivative is because when the similar process of proving that, we can't say that the secant is always the secant is always positive in a particular interval. So the secant, inverse secant rather, and the inverse cosecant derivatives, you would still have that plus minus that you have to leave in. So we look at the absolute value instead. And again, this is just how do you take the derivative of a function when the outer function is an inverse trig function. What we're not seeing here is the chain rule explicitly written out. All of these really have hidden the chain rule where we take also the derivative there and multiply it by the derivative of the argument. So, just for example, the derivative of the inverse sine of, let's just say f of x, I think that's what we've been using, is 1 over the square root of 1 minus the function squared times the derivative of the function. So all of those are really chain rules if you think about that all of them are really multiplied by the derivative of x, or the derivative of the argument. Does anyone have any questions about that?
So in those cases, you're not evaluating, you're not including the 2, the exponent of 2 for f prime?
No. Just
Why
the
is that?
argument. That's just the way that they happen to unfold. The f prime there is just a result of the chain rule, not the result of the derivative of the inverse sine of something. Okay, so for example, if let's say y were the inverse sine of 2x, By the way, maybe you remember when you actually looked at like how to solve inequalities. So I guess one of the ways those actually show up is, for instance, if we wanted to know what is the domain of the inverse sine of 2x, right? What is the domain for the log of x squared minus x plus 2? So you have to say that, like, for instance, we're taking the inverse sine of 2x, but we said that the inverse sine of anything had to be between -1 and 1. So we would say that 2x has to be between in between and inclusive to -1 and +1. So that's where you would see certain types of inequalities. So the domain of this function is all values that are in between -1/2 and +1/2. There's no other outputs, or sorry, there's no other inputs and/or outputs for values outside of that interval for the inverse sine of 2x. Yeah.
So you basically just divided, it's just got the x to be alone, correct?
Yeah,
So
just-
you divided 2 on both sides.
Yeah.
But if you divide with an equality, don't you flip the sign? No.
Only if you're dividing or multiplying through by a negative.
Okay, gotcha.
Yeah.
So if it was -2, then you would flip the sign.
Correct.
Then in that case, it would just still be the exact same thing.
Yeah.
Okay, cool.
Yeah. So I mean, like, whatever. What if it were like a question that said, what's the domain of the inverse sine of the natural log of x? Right? Then you got to solve another, right? You solve this inequality. When is the natural log in between 1 and -1? So anyways, that's, maybe you saw that, maybe you didn't when you were looking at these functions. So I think it is somewhat important to know. I'm not going to ask you on the exam what's the domain for these things, but I think it's important to know, to have a general idea of like where my inputs are. But the derivative of the inverse sine of 2x, it's 1 over the square root of 1 minus the argument squared times the derivative of the argument.
It's using that chain rule, but it's essentially separating your, I guess your trigonometric term and what's inside the parentheses.
Yeah,
It's
exactly.
almost treating them as two separate multiples.
Yeah.
Okay.
Yeah, same thing with the logarithm, right? When we do the 1 over, that's the only derivative of the logarithm that we have. We do 1 over the function, and then when we say times the derivative of the function, that's because of the chain rule. So times the derivative of the function here, again, because of the chain rule. So the 1 over root, that's coming from the inverse sine.
Just out of curiosity, is that is treating those as separate terms or separate functions, however you want to look at it, is that like mathematically correct, or is that just kind of something, the way it needs to be treated in order to get the result?
It's both.
It is
It's
both.
mathematically correct to think about those as two different functions. They wouldn't be two different terms. Terms are separated with addition and subtraction.
Okay.
So two different functions is correct to think about.
Okay.
Because remember, the chain rule operates on a composition of two functions,
Right.
or two or more functions. So like, what I'm really looking at in terms of the chain rule is that I have the inverse sine of u, where u is 2x. So one function is the inverse sine function, and the other one is 2x. Yeah, I think that's exactly how we're looking at these. Maybe we didn't explicitly state it, but
No, I don't think it's, that's the only reason I brought it up, because I don't think it's ever been, I don't think, that I can think of anyway, in any math class where we've, thought of those as separate functions.
Right.
There's always one function and one function only.
Yeah.
So that's kind of why I was curious. I wasn't sure if,
Okay.
if you could, if there was correctness in seeing them individualized.
Yes.
You know.
Yeah, any composition, you can look at it as an individual function. Like any composition, like if I say, like even if I just look at this thing right here, the square root of 1 minus x squared,
Right.
that's two separate operations going. You've got the 1 minus x squared function and the square root function. So really what happens, the way we look at it as a whole function, but what's happening is when you plug an x value in there, you've got to compute 1 minus x squared first. So like if I'm plugging in all these numbers, I apply 1 minus x squared first, and then I get these numbers,
Right.
and then I have to take the square root of those numbers to get what the square root of 1 minus x squared actually is. So if we've got 2 over the square root of 1 minus 4x squared. That's the derivative of the inverse sine. So just be mindful, we said the domain of the inverse sine of 2x was the closed interval from negative 1/2 to 1/2. When we talk about the derivative, is there some numbers in that interval that are issues with the derivative itself? Hmm?
1/2 is a problem.
Yeah, 1/2 is a problem because 1/2 squared is 1/4.
1 minus
Times-
1.
Yeah, and minus 1/2 is a problem. So just like here where we said the domain of the inverse sine was negative 1 to 1 including, but the derivative goes from negative 1 to positive 1 not including. So our derivative here would go for, and we can just make a note of this, for x in the interval negative 1/2 to positive 1/2 not including. So how about take a moment and compute the derivative for the inverse sine of the natural log of x.
I said it's probably not right. X to the square root of 1 minus x squared. That's what I got, and it makes sense when you saw this.
No, I was just making sure. I just wrote mine. Mine still has the 1 over x on top.
Yeah, but remember it's 1 over 1 minus that.
So,
You had like 5 minutes after class.
Yep. Yeah, that's fine.
So I just want to make sure these settings are right, that's it.
Here's the issue.
This one's straight.
Here's the issue. I understand where you're coming from,
Because we
but
would just do.
because the numerator is something minus something, nothing can
Oh,
be
because the
canceled.
squared is part
You
of it.
can't just cancel out.
No, you don't
Breaks
cancel.
down.
Yeah, you don't cancel.
Oh, yes.
Where I think that it's getting, that what I think that the issue is I think that H needs to be multiplied out of the
You can do it that
final
way too,
denominator.
absolutely.
I think I was working a little bit too fast for the way I was.
Well,
Yeah,
also,
you can multiply everything by 1/h.
yeah,
And that gets rid of the h, then you don't have to worry about it.
Okay.
yeah.
So the derivative of the outer is 1 over the square root of 1 minus the argument squared. Then we have to multiply by the derivative of the argument. Is everybody all right with that? Are there any questions? And the derivative of the natural log of x is 1 over x. So we have 1 over x times the square root of 1 minus ln of x squared. Now, be careful, because when I say the ln of the quantity x squared, I can say that's 2 ln x. However, the natural log of x squared doesn't fit that property, because we're not taking the natural log of something raised to a power. We're taking the natural log of something and then raising all of that to the power. So sometimes the natural log is written like your sines and cosines and stuff, where it's like that, just so people, I guess people won't make that mistake of putting the 2 out front. Because these two things, this is not equal to this. So just be careful with what you do there. Okay. Any questions on that example?
Nope.
Yeah.
If you were to figure out which x values would be which x values would be like 1 over?
For the denominator? I mean, for the derivative, rather?
Domain.
The domain of the original function.
It would still be negative 1 to 1, not including?
Right, but remember, that's for the sine of something.
Yeah.
So the natural log here has to be between negative 1 and 1.
Okay. But then you would solve for your x. But you can't really do that?
Yeah.
Like that's what-
So the argument of the inverse sine has to be in between negative 1 and 1 for the domain, right? So how do we get a grasp on what x can be, not what ln of x can be?
So would you do e to the negative 1 and 2?
Yeah,
And then not including would be your
for your derivative, yeah. So we would just exponentiate both sides. That means e to the negative 1 is less than or equal to x, which is less than or equal to e. For the domain of the original function, the derivative would then come in and exclude those endpoints, e to the negative 1 and e, right? Because if we look at the derivative, we have the ln of e is 1, squared is 1, 1 minus 1 is 0, and the ln of e to the negative 1 is the ln of e to the negative 1 squared. Again, minus 1 is the square root of 0. Okay, so or we should say our derivative then is for x values that are in between e to the negative 1 and e strictly in between those two. So if we look at it like, here's arc sine of, or inverse sine of the natural log of x. Let's just put our e to the negative 1 here. So see that gives us the boundary on this side, the 0.368. And if we did e to the first, where's that at? Oh, That's right there. Does that make sense? Okay. So we're just visually verifying that what we said, that the inverse sign of natural log is in between e to the -1 and e to the 1. So then why does it make sense to exclude these values from our derivative?
Because they'll result in a zero denominator, I assume.
Right, so analytically or mathematically, they result in us dividing through by 0, but if the function's defined at that point and we say, what is the derivative at that endpoint right there? So like, what's the derivative right here at this point? We can't compute that because it's only one way. We can only say the derivative from one direction. What is the derivative at this point is that slope, and that slope, and that slope, and that slope, and that slope. But since we can't come from this direction because there's no function, it just stops. It doesn't make sense to have a derivative right at that endpoint. There are things, there are one-sided derivatives, but they're defined like really weird and they don't have much practical use. So we don't see those or deal with those, but you can look up one-sided derivatives if you want. But that's why the derivative doesn't exist at the endpoints, because we can't approach it from both sides.
So continuity does not, or I guess a derivative is not bound to continuity?
So, right, so that we had a theorem that connected continuity and differentiation together, and what was it?
I say it to myself like one day, I swear to God, it's like, isn't it?
If you're continuous.
Differentiating can equal continuous, but continuous cannot equal differentiating.
Yeah, so remember the absolute value is continuous at 0. Can we find the derivative at 0?
No.
So this is continuous at 0, but it's not differentiable at x equals 0. So what does that mean again about the connection between derivatives and continuity? Does continuity imply differentiability?
No.
No, clearly from this example it doesn't. Does differentiability imply continuity?
Yes.
Yes.
What was that called again?
Theorem 3 something.
Theorem 3 something.
Differentiability implies continuity. We also looked at the converse, where we said if it's not continuous, it's not differentiable.
You're like, today is Thursday, so it's Thanksgiving.
Yeah.
There's not a word for that?
Yeah, I forget the logical. They call it a, what do they call the argument and the antecedent or something like that? Yeah, I forget. So yeah, even though the function's continuous at that endpoint, it isn't differentiable at that endpoint.
Okay, so you're like going back to the very beginning, we have that looking at a limit, approaching it from the left versus the right. The limit as x approaches that value, if the coming from the left and coming from the right do not equal the same, then we say the limit as x approaches that value does not exist.
Correct.
Right? But if the value, or if the limit as x approaches 0 does not exist, that does not exclude the possible existence of a derivative at that point as that x is approaching.
So
Does that sound right?
So then you would say that the function is not continuous because the limits don't equal, right?
Right.
But if a function's not continuous somewhere, you can't define a derivative there. Like just even the most straightforward case, like this function is not continuous there.
Right.
It wouldn't make sense to say what's the slope of the tangent line at that point because there is no point there, right? There's a gap or a break. Right
Okay,
there.
and that's different than like looking at the vertical asymptotes, like what we're looking at.
Right.
It's a different situation.
Yeah, vertical tangents are undefined because that's when your derivative is you're dividing by 0 in your derivative, basically.
Right.
Yeah.
Okay.
Yeah, but we see the graph here, like we said, the inverse sine function is continuous at that endpoint, but it's not differentiable at that endpoint. Kind of like this. This function's continuous at that point, but it's not differentiable at that point. if we could define the derivative at that point, we could certainly say we know it's continuous. So if it's differentiable, if we can take the derivative there, it has to be continuous there.
And you're saying technically we can, in that case, with
And-
what we're looking at, if we wanted to, we could find a derivative. At that point where you have, say, just the circle.
Yeah, but it would have to be a one-sided derivative,
Okay,
which we don't look at or talk about.
okay.
So yeah, that's, technically we could. We would say the derivative as we approach that point from the right is equal to, but then that's a whole nother can of worms. Okay. Yeah, but certainly good to connect those dots. I think it's important. Let's look at this example and then we'll call it quits for today. How about the cosine of the inverse sine of x?
Of course you want to do that.
Yeah, I mean, you could like test yourself. You could like make up functions on your own and say, can I find the derivative of this function? I don't know if you're that nerdy or not, but I think it would be cool. So here the argument is inverse sine. So when we take the derivative initially, we're only taking the derivative of the outer function cosine. So the derivative of cosine would give us negative sine. So we have negative sine. We're leaving the inner function alone. Oops. Inverse sine of x. Then we do what?
Times the derivative.
Right, exactly. Times all of that multiplied by the derivative of the inverse sine of x. Which we already know, or we've already seen. Maybe we don't know it at this point, but that derivative is just 1 over the square root of 1 minus x squared. What is the negative sign of the inverse sine of x? Negative x. So all of this stuff we can simplify algebraically to negative x. So our derivative is simply negative x over this root. Because the inverse sine of x, inverse sine of sine, or the sine of inverse sine of something is always that thing. It's like E and ln.
So essentially you're saying it's like multiplying by the negative version of itself.
Not really multiplying by the negative version of itself. It's like taking the square root of a square. Now there's another way to do these. Do y'all remember in pre-calc or in trig where you were given us an expression like cosine inverse sine and had to rewrite that in terms of x? Yeah. So we could also do it that way. We could say, well, I don't like this function as it is, right? To me, that's weird, and we don't see those things often. So what we could say is like let's call the inverse sine of x. Remember, the inverse trig functions output an angle. So let's just call the inverse sine of x theta, and then so y is really just the cosine of theta, where inverse sine of x is theta, which means that x is what? Not negative. We would. How do we undo the inverse sign? We take the sign. Yeah. So if x, or sorry, rather, if sine theta is x, it's x over 1. So sine of this angle is the opposite over the hypotenuse, right? So the other side is found by Pythagoras' theorem. You find that to be the square root of 1 minus x squared. So what's the cosine then? Here's the theta. What's the cosine of that? What's cosine of theta? Adjacent over hypotenuse. So cosine of theta is actually just the the square root of 1 minus x squared. In other words, the cosine of inverse sine is 1 minus x squared. What's the derivative of 1 minus x squared to the 1/2? It's 1/2 times 1 minus x squared to the negative 1/2 times negative 2x. The 2 and negative 2 divide, so we just have x over the square root of 1 minus x squared. Negative x, sorry. So it's the same thing.
Just like that.
Same derivative, just another way to think about it. So for whatever that's worth, again, if that's confusing, then just remember the derivative we just did. No need to know two different ways, but it can be helpful. All right. See you next week. Have a good weekend. Oh, would anybody like a 3.6 handout? I have 5 of them.
They're on D2L, right?
They are in D2L. I just had extras if you don't want to spend money printing them.